Let's look at how to model motion using parametric equations. The first thing to note is we want to know the position of an object. And so perhaps we're in two dimensions, like a y and an x-axis. And for this scenario, let's say we're at a museum and we're looking down with a bird's eye view. And let's say there's a person who starts at the point, let's say right here we have 0, 5. And let's say they're looking at a painting on the wall. After some time, they walk to a new position. And let's say that that position is the position 2, 4. And maybe there's like a statue that they take a look at. Sometime later, they walk to a new position. Let's say that position is 5, 4. Maybe they're looking at the wall and there's another piece of art on the wall. And then let's say after some time they walk to another piece of art and take a look. And let's say that that's at the position 5, 1. And so this is from a bird's eye view, sort of looking down and letting the floor be an XY axis, a grid. And what we can see is that the position of this person and the path of the position is shown here. What's not shown is the time at which the person was at each position. We can see the direction that they traveled. We can see the positions that they were at and the positions they walked through in between, a set of points. But there's this hidden parameter, time. And we could break down each part and say, okay, this looks to be a linear function. This looks to be a constant linear function. This looks to be linear. We could maybe write like a piecewise function for each portion of their journey, and we could show their time compared to their x position compared to their y position and how those things were changing. But the idea I want you to have is that this is their position. On the graph of y versus x, we see their position. Time is hidden. And so I actually want to do a different example because I don't want to do piecewise. I want to do something a little easier to work with algebraically. So let's imagine that there is a boat on a dock. And let's position this dock at the coordinates 0, 1. And we'll say, here's this dock. And we'll say there's this boat, and the boat will just be a point. Right, there's my boat. And let's say this boat is going to travel to an island. And let's say the island is somewhere over here. And so looking down on the pond or the lake that we're on, we can create this XY coordinate grid with X and Y, and then we can define the position of this boat based on its X coordinate and its Y coordinate. And so we're just finding this dock. We sort of located it at 0, 0, and then the corner of the dock where the boat's parked is 0, 1. And let's say this boat heads to the island. And let's say it goes through this path here. So it goes to this coordinate here, 2, 0. Let's say it goes to this coordinate here, 4, -1. Let's say it goes to this coordinate here, and we'll call that 6, -2. And the path that the boat is taking is in this direction. So the direction that we travel is interesting or important. And let's say this island also has its own little dock here. So at 6, -2, we make it to the dock, and we get off on the island, and we have fun. So let's say we want to actually model the path of this boat on this trip for some parameter time. So what we can do, and let me shrink down this so we can have room for a table, is we can create a table of values, and this table of values can show you the time compared to the x position of the boat compared to the y position of the boat. And so at the very start, at time equals 0, the boat is at the position 0 on the x-axis. We're at 0 from side to side, and 1 on the y-axis. And so that locates the coordinates of the boat. And then we can see sometime later, this boat makes it to the point 2 on the x, 0 on the y. So on our coordinate grid, we can see we've traveled to this point. And now let's say this is a speedy boat, and let's say this only took us 1 minute to get there. Then let's say, so this right here took 1 minute. Then let's say at time equals 2 minutes, we made it to the next coordinate, 4, 1. So we have 4, negative 1. So at some point we make it to that coordinate 4, negative 1. It takes us a minute to get there. We're going in a constant direction. And then at t equals 3 minutes, we make it to the coordinate 6, negative 2. Pay attention to the fact, by looking at this graph, there is nothing that implies what the time is. Time is a hidden parameter. It could have taken us half an hour to get to the island. It could have taken us 2 hours. It could have taken us 30 seconds. Like, we don't know. That's why time is this hidden parameter. I'm sort of making it up for the example. All we know is that we have a set of xy positions, and they exist at some time t. And so for this example, now that I know my parameter, the time, I can actually write a set of functions that model this scenario. So I can model the x position of the boat, which I'll call x of t. If I look at the x function, I can see I'm going plus 2, plus 2, plus 2 every time I go 1 for the time. So it's clear that it's a linear function. It has a slope of 2, 2t. My initial x coordinate is 0, so I'm going to write plus 0, but I certainly don't need to write that. For my y function, I can see that y of t is equal to, well, we're going minus 1, minus 1, minus 1. We have a constant change in y as t changes by plus 1, plus 1, plus 1. So this is clearly a linear function with negative 1t, and my initial y position was 1, so I'm going to write plus 1. And so now I have two functions that can model the x position of the boat at time t and model the y position of the boat at time t. So let's say I wanted to know where the boat was in the x direction at 30 seconds. I could plug in x of 0.5 for my time, because time is measured in minutes, half a minute, 30 seconds. And I can say that that is equal to 2 times 0.5, and then I don't really need the plus 0. X of 0.5 is going to be equal to 1. And so that tells me that at 30 seconds, my x position is 1. And I could also figure out the y position at that time if I wanted to. I could do y of 0.5, and I could say negative 1 times 0.5 plus 1. So y of 0.5, the y coordinate at 30 seconds, is going to be 0.5. And so I have this coordinate 1, 0.5 that I was at. And the time, you can't see it on the graph. There's nothing here that implies the time. But the time of that position was 30 seconds. So the time is hidden. And I could also do that just with like the y coordinate. If I only cared about the y, I could say, well, at 2.1 minutes, I could do like y of 2.1, where was the boat? And then you could plug that in and say, okay, well, that's negative 2.1 plus 1. So y of 2.1 is negative 1.1. And so that means at time 2.1 minutes, the y position, based on this grid we've defined, is negative 1.1. So this is all information you could gain from this. Now, the other thing to note is our parametric equation this one goes in the proper direction, right? As I increase my parameter t, I move along the path of the boat. But I should probably put a domain restriction. So my domain for t is going to be between 0, my start, and it looks like my journey ends at 6, -2, which occurs at 3 seconds. So my set of parametric equations are going to be this, with domain time is between 0 and 3. The other thing I could do is say I just want to model this position function. So say I want to know what my y position is for any given x position. Well, what I can do then, let me shrink this down. Third time's the charm. Almost. Lost a little bit, but that's okay. Put that one on there. Oop. What I can do is I can eliminate the parameter. And eliminating the parameter allows me to know the y position that corresponds to a given x position. Okay, so if I want to know the y position corresponding to an x position, really this is going to give me the actual curve or the line, the graph, I can eliminate the parameter. So we said x of t, which now I'm just going to say x is equal to 2t plus 0, so just 2t. And we're going to say y of t, but y is equal to -t plus 1. So to eliminate the parameter, I solve for t. T is x over 2. I take that, I substitute it in for my parameter time, so I get y is equal to -x over 2 plus 1. And this is my equation that models the y position that corresponds to a given x position. Now I could set a domain restriction on this if I wanted this to purely match the path of the boat. So I could say x has to be between 0 and 6. So that would make sure it's only this piece of the boat. But this allows me to know the y for any x or the x for any y. So I could plug in, for example, like, oh, when x was 2, where was my y? So I could say y equals -2 over 2 plus 1, which means y equals -1 plus 1, which is y is 0. So that means I must have at some time been at the position 2, 0. And voila, we were. So that's the main idea here. Now there's two more things I want to show you that we can do. So let me erase a lot of this. Actually, no. Let's say we wanted, let me copy and paste this. Okay, let's say we wanted to do this same trip, but let's say we have a return trip that we're going to make now. Let's say we are going to go back. So instead of going along this path towards the island, let's say we're now going to reverse our path and go back from the island. So we're actually going to go along the path this way. Same exact path we're going to take home, but let's say we go the other way. Well, in the forward direction, we had our equation, and we had our set of times and distances. What we can really do is to turn our curve around and go backwards is we can take our original functions, x of t equals 2t, and we can say y of t, which is equal to -t plus 1. And if I want to just change the direction of this curve, I can make this negative. So I can say x of t is equal to 2 times -t, and y of t is equal to -t plus 1. So this is going to switch the direction of my curve. And so what we might get something like x is equal to -2t, and y is equal to t plus 1. And so this is going to swap the direction that my curve goes. But it's not necessarily going to model exactly what I want it to model, depending on the domain. Because if I just go ahead and plug in some points here, like t, x, y, at t equals 0, x is 0, and y is 1. So the problem is this is still starting me right here. And then I'm going to actually go in this direction. So we could do 1, and then at t equals 1, we would end up with -2, and then we'd end up at 2, and so that would be this point here. So we're actually changing the direction of the curve, but we're also changing the actual path we're going, because we're using a different part of the curve if we're only plugging in t equals 0, t equals 1. So we'd probably want to actually offset that if we were modeling a real boat. But really what I want you to just see is the fact that I can change the direction that the boat is going by changing t to -t. If I change the parameter, if I flip the parameter of some curve, I can change the direction that we're going. And we'd want to reset this so that at t equals 0, we're actually here. So I could play with a domain of t. I could kind of say maybe t would have to be, well, in this case, t would have to be between probably -3 and 0. And so that's a little weird for the purposes of modeling a boat. Why would you have a negative time? But that would actually get us the portion of the graph we want. At t equals -3, we'll have x is -2 times -3 is 6. Y is -3 plus 1, -2. I could plug in -2, -1. 0 we just did. We knew that was 0, 1. -2 we should get 4, comma, -1. And this we should get 2, comma, 0. So if I use the proper domain here, I can get the actual coordinates of the travel back. It is a little weird to use t equals -3, so maybe you just create a whole new parametric equation if you cared that much. But the really important, the key thing, you might say, is that I can change the direction of this curve. I changed it from going this way to this way just by making t negative. Similarly, I can change the speed of my curve. So let me paste back in my graph here. If instead of being 1 minute per section, I wanted it to be more, like I've got this set of x and y coordinates, and I've got a time. We know for a fact we're going through all of these points. These are the points that model the path of the boat. And before we had let me see. All right, we set our parameter of time and we said 1 minute per I don't know, that was what we were taking up by, 1 minute per key coordinate that we had. But if we wanted a much slower boat, we could tick our time by 0, by maybe it takes us 5 minutes, then 10 minutes, and maybe this is a 15-minute boat ride. And so in this case, I could have basically the same parametric equations. X of t was equal to, originally it was equal to 2t. But if I want to go 5 times as slow, if I want my journey to be 5 times as slow, I can say x of t equals 2, and then I can use t over 5. And I could equivalently call that x of t is 2/5 t. Now, if I use the actual sort of slope of the line, that's very easy to see. I'm going plus 2, plus 2, plus 2, compared to plus 5, plus 5, plus 5. But I don't even need to do that. Like if I want the boat to go 5 times as slow, I can just plug in t over 5 in place of where t originally was in the function, and now I've modified it so that whatever t I put in, I've actually divide that by 5 and I'm going slower. If I want to go faster, I could say x of t, and let's say I want to go 10 times as fast is equal to 2 times 10t. So now I'm going to go 10 times as fast on this journey, and that could be equivalent to 20t. So there's ways you can use the parameter t to represent modifying the speed and the direction. So those are kind of some of the basics of modeling motion using parametric equations. You have position, hidden parameter time, Included in that will be a direction. We can modify the direction by making t negative, although for actual modeling, like you might have to consider its domain and whether it actually makes sense. But you can also modify the speed that the path is tracing by modifying the time component. And those are sort of the main ideas to start for modeling motion with parametric equations.